Let me just make sure is it coming up my screen?
Yeah, it's coming. Yeah, it is coming.
Okay, good.
Great morning, all. It's my pleasure welcoming our speaker, Dr. Murthy, in this late night, actually, for him. Welcome you, sir. And I also welcome our advisor, Dr. G. Sambandhan, and all the participants for this day 5 session. Welcome you all again. So with this, I would now request our advisor to introduce our speaker and welcome him. Over to you, sir.
Thank you, Dana. Good morning to everybody. Good morning, Dr. Ieee Murthy. I take privilege and it is my honor to introduce Dr. Murthy Ieee, who is giving the lecture today on cyber security of electric power distribution systems. He has been with Beckwith Electric since 1989 and presently holds the position of the president. He received bachelor's in electrical engineering from Jawaharlal Nehru Technological University, Kakinada in 1981, master's in electrical engineering from IIT Kanpur in 1983, and a PhD in electrical engineering from University of New Brunswick, Canada in 1987. In 1988-89, he taught and conducted research on digital power system protection at Memorial University in Newfoundland, Canada. He has published several research papers in international journals on digital protection. He holds 6 US patents in the areas of digital controls and protection relays. Dr. Ieee has been appointed as the chairman of the International Electrotechnical Committee, IEC, Geneva, Switzerland, Technical Committee 95, measuring relays and protection equipment from 2015 until 2021. In this capacity, he provides leadership to experts from national committees of 34 countries in the development of international standards. He was a US delegate to the SIGRE Paris, France working group on modern techniques for protection and monitoring of generating plants' power transformers. He was a member expert of the NERC, North American Electric Reliability Corporation for System Protection and Control Subcommittees, SPCS. He also served on the Merit Review Panel of US Department of Energy project in 2012 and 2015. In 2006, Dr. Ieee was elected to fellow grade by the IEEE Fellow Committee for his contribution to computer relays and power system subjects. He is the vice chair of the IEEE PES Power System Relaying and Control Committee for 2019 to 2020. He was also chairman of working group which developed IEEE standard C37-102-2006 guide for AC generator protection and co-authored an IEEE PES tutorial on protection on synchronous generators. He was the organizer of the IEEE PES tutorial on distributed voltage and VAR control and optimization in 2015 and 2016 PES general meetings. He was also presented and organized tutorials on cyber security of electrical power transmission and distribution systems, IEEE PES General Meeting, Chicago in 2017, in Denver in 2018, Atlanta in 2019, and Montreal in 2020, and in Distributed Tech in 2019. He chaired the working group which received the IEEE PES Working Group Recognition Awards for an outstanding technical report application of peer-to-peer communication for protective relaying at the Denver meeting, Colorado in 2004. He received IEEE Florida Council Outstanding Engineer, Florida Engineer in 2005. Dr. Ieee received IEC 1906 Award in 2010. This honors IEC experts around the world in recognizing their exceptional recent achievements and contribution to the IEC committees. He also received the Indo-US Chamber of Commerce of Businessman of the Year Award in 2013. Very wonderful personality, and I take pleasure in inviting and handing over the platform to him to deliver this lecture. Thank you, sir.
Thank you, Dr. Sambandhan. I think it is a great pleasure to come in and speak. I think 2 weeks ago, Dr. Sambandhan contacted me and said, would you be able to speak on one of the topics that he's organizing a training? And then I haven't seen him in a long time, and I thought maybe I'll see him through this lecture. So I said, okay. And then the topic, obviously, is cybersecurity, which I already taught in the past. So I put together a presentation, and hopefully you folks are going to get what you're looking for. I'm going to leave a few minutes for questions towards the end. Generally, most of the teaching is done through question and answer session towards the end. So I'll try to give enough time. If you want to ask any questions, please wait until the end, or you can send it through the chat line so Dr. Sambandhan can read those questions towards the end so I can answer them. Okay, let me just take off my camera thing here, because it uses up the bandwidth and creates a problem sometimes. Take this thing off. Okay, good. Go back to the share. Okay. Somehow it's went back there. Let me see. Oh, cyber. Somehow this big part thing. Okay, can you see the screen now? Hello?
So we are able to see your PPT
Okay,
mode.
good.
Yeah.
Okay. Okay, so just to give you some general idea about outline of the presentation today, I'm going to give some basic definitions of cybersecurity, physical and cyber infrastructures. I'll talk about some risks, including some definitions of various viruses, worm attacks, Trojan, keyloggers, denial of service attack. I'll talk about cyber assets, and then how do you manage these cyber incidents. So after that, we'll talk about industry standards and cybersecurity from IEEE, IEC, and then NIST, which is in the US, National Institute of Standards and Technology, and then NERC. And then we'll also discuss things about cybersecurity of distribution, protection, and control IEDs. I think the topic here is mainly distribution side based on my understanding. So that was the reason I picked the distribution system. How do you protect it? I'll also talk about Ukraine attack. There was a cyber attack in 2015 on Ukraine from a foreign source. I'm going to explain about what happened that time. And then I'll also simulate a cyber attack on the war.
Excuse me, sir. Can you just put it in the slideshow mode?
Oh, it's not moving on?
No, sir. No. It is not in the slideshow mode.
Oh, maybe I picked up the wrong one. Let me see. I got two things in here. I've been moving on there. This one. Let's see here. Do you see it now or no?
No, sir. I think it may take time.
Let me see here. Let me close this. And then what I'll do is I will unshare and then share it again. And then this time I'll have to pick the PowerPoint. And then I'll click this. So it's working now?
Not yet, actually. We could see your slides, but it's not in the slideshow mode.
Wow. So you can only see the slides basically. That's why you can, but let me see here. Maybe I have to share the screen rather than sharing the point. Let me see. Unshare it. Share it again. I got to see the desktop. Okay, maybe that's what it will be. Yeah. Okay. Now go back to here, and then try this. Can you see it now?
Yes, sir. Yes, sir.
Okay, good. Good. Okay. That's good. Okay, so I was just going through the table of contents here. So if you look at the last section here, cybersecurity of distribution, protection, and control IEDs. So if you look at any distribution system, you have distribution substations, and then you have outside the substation distribution feeders going along, and then you have a lot of devices on the distribution system. Inside the substation, you have protective relays, controls. Outside the substations, you may have reclosers or capacitors, voltage regulators, DER interconnections, distributed energy resources, all kinds of devices. And most of them have communications nowadays. So we'll take one example of a capacitor control and then see how it can be protected against cyber attacks. We'll talk about IEEE 1686, one of the IEEE standard for cybersecurity. We'll also talk about how do you manage passwords using Radius Password Management Server or Ldap. There's another software that is used to manage the passwords. We'll also talk about role-based authentication to secure the devices. And at the end, we'll also talk about IPsec, which is basically VPN tunneling. How do you actually VPN it to the devices directly, which are in substations or outside the substation on a pole someplace through a radio modem connected to it. And then finally, we'll conclude with some comments. So looking at two different infrastructures for electric power system. So if you go all the way to the generation power plants, these are typically very large, either fossil plants or hydro or nuclear or gas turbine, any kinds of large power plants. They are generally remote. You got a transmission line, which is transporting all that power to nearby towns. You got this voltage step up here and step down here, and finally comes to the distribution voltages. Could be in India, I think 11 kV, and then comes down to 230 volts or 400 some volts. In the US, we use mostly 120 volts in the neighborhoods, and then distribution voltages anywhere from 4 kV class, 15 kV class, 22 kV class, and 34, 5 kV class. These are the distribution voltages in the US. So those distribution substations get connected to residential, commercial, and industrial loads. So this is the physical infrastructure that you have. Now looking at the cyber infrastructure, you got a control centers, which is controlling the power plants. And then you have RTOs and ISOs, independent system operators. They're monitoring the power flow and also regional transmission companies, and they are exporting power back and forth to the transmission lines and controlling them. And on the distribution side, you have a distribution control center. They typically use DMS, distribution management systems. And then all of them are interlinked through communications. Whether it is wireless or wired, it doesn't matter. But they are communicating back and forth so that the power is generated and then finally supplied in an appropriate and optimal manner. So your cyber and physical assets are shown here. So in order to make sure that the power system operates reliably, in the olden days, only physical threat used to be there. You've got the security guard at a power plant. Maybe there is a fence near the substation. There may be some monitoring cameras that are there, but there isn't any cyber threat because there was no interconnection or communication media in the past. But if you look at in the last 20 years, the communication is, I would say, more than half of the substations have pretty good communications. In Europe, it is even more. In India also, I think a lot of communication infrastructure is increasing. And the majority of the infrastructure spending in the world is happening in the distribution side nowadays, and a lot of them is in the smart grid area. NIST, which is the National Institute of Standards and Technology, the smart grid infrastructure diagram, they way back more than 10 years ago, they developed this. This particular one basically maps out interaction between physical and cyber assets that you have. So you got on the left top, you got markets. So you got aggregators, retail wholesalers, ISO, RTOs, and then you've got operations, which has RTO, ISO operations, transmission operations, and distribution operations. And then you got service providers, utility providers, third-party providers. And then in the bottom, you got bulk generation. These are large power plant control systems, large generators, and transmission and distribution. And then DER, distributed energy resources, all the solar, wind, whatever customer-owned generation. And then finally, all this stuff is the main purpose is to serve the customers. You got customer EMS, customer equipment, appliances, thermostats, electric storage, electric vehicles. So all of them are interconnected overall. With the smart grid, the communication bandwidth requirements have gone up dramatically. Also, just wanted to give you some general idea about the technological evolution in the utility industry, especially in the substation area. If you look at a conventional substation on the left, you'll see a lot of wiring going from control house to the yard, switch yard. You got a circuit breaker, current and voltage transformers, you got disconnect switches, transformers, medium voltage switchgear, all kinds of heavy equipment, but it is connected through physical wires going underground back to the control house here. So there isn't any cyber threat at that time. There is only physical threat. I remember in San Francisco area several years ago, there was a physical threat. People used shot with guns. Some of the substation equipment caught on fire. It was a major thing. But nowadays, most of the warfare is fought with cyber. So if you look at the evolution now, most of this wiring, physical wiring, control wiring is replaced with fiber. Except for heavy power wires that needed, like a substation battery has to go to the yard to feed these. Majority of the other communications, whether it is the contact inputs or the CT and VT, sampled values are probably sent through the fiber, going to some control house here. So it is possible for hackers to come into any of these communication networks, either wired or wirelessly, and then cause severe damage. So that is the main reason why when people have started to use Ethernet architectures in substation with open protocols, like IEC 61850 or IEC 60870-5 or DNP or Modbus, or one of those protocols, then it brings the cybersecurity risks. So that is the major problem facing the whole industry nowadays. Just to give you a basic definition of this risk thing, security, how you define security, the facet of reliability that relates to the degree of certainty that a relay or a relay system will not operate incorrectly. What happens if a relay operates incorrectly? If there is a fault, the main purpose of the relay is to detect that fault and operate the relay, go and open the circuit breaker to isolate the faulty system. If it incorrectly operates, that means it did not clear the fault, you'll see the smoke coming out from the switch yard. But if suppose, let's say it acted erroneously and tripped off a large power plant, a gigawatt power plant, then nearby city will be blacked out. So both any incorrect operation, whether it is not operating when it should or operating when it should not, creates a problem. So if a hacker hacks into the network, he can cause those kinds of actions, either by changing the settings or disabling the functions or disconnecting the communication, all kinds of stuff they can do. So that's why it is important, in order to keep the reliability, the security of these devices is very important. There are various ways people can attack. There is a physical attack, as I said, the machine gun attack that happened in California several years ago. EMI, electromagnetic interference. People can put out very strong electromagnetic field. Some of these digital devices will start misoperating, or electromagnetic pulse in the upper hemisphere. They put this like a warfare basically, that can pretty much disable all electronic equipment or make them non-operative. The last one is digital. That's where the topic for today is the cybersecurity related things. So there are a lot of issues here. You can have a misconfiguration of the device, vendors bringing in stuff, manufacturers bringing in and then bringing the viruses along with it. An insider accidentally punches some buttons to trip the whole substation. It happened in Florida maybe 8-9 years ago. Somebody was doing something by accident. He touched something, the whole substation went dark, and the particular utility was fined by NERC. I don't remember how much. It is several $100,000. Intentional insider. That means somebody is really hating his boss and he doesn't like him. He wants to create a big problem. And then he goes and hacks into the equipment that he's supposed to operate on, and then goes and trips a power plant or doesn't trip when it is supposed to trip. Hackers which are outside could be inside the country or could be coming in from other countries, navigating through the internet, trying to figure out what ports are open. And the moment they find it, they try to attack those devices that are connected. The last one is nation states. There are state-sponsored terrorism or cyber warfare. There are rogue nations in the world. The main purpose for them is to deploy these hackers who are actually trying to attack other countries, their electric infrastructure and oil, all the banking, you name it, anything that is interconnected, they'll try to attack. So that's why cybersecurity measures are very important as the grid is getting connected more and more through communications. So let's talk about different malwares that are possible to attack these computers that we're talking about. The first one is a virus. A virus is a piece of software that infects a legitimate program and replicates and spreads to other computers when activated by a user. As an example, a computer virus hits the US drone fleet. The computer virus has infected the cockpits of America's Predator and Reaper drones, logging pilots every keystroke as they remotely fly missions over Afghanistan and other war zones. And that was the reported incident. It happened. Hackers got in. Recently, GPS spoofing crashed a drone. Somebody created their own GPS, very strong signal, and then miscoordinates were put in. Rather than flying, it went down. And so you can actually click on that web link to read more about these incidents. The next one is a worm. A worm is similar to a virus, but are self-replicating and will spread to other computers automatically. It doesn't have to be activated by a user or anything. They spread automatically. Example, variants of a ransomware, also called Stuxnet. This is specifically designed to attack control systems, attack SCADA systems and PLCs. Quite a few nuclear plants in certain countries were attacked by this Stuxnet and created several severe damage. And also because SCADA systems are heavily used in electrical infrastructure, they could cause a severe damage there also. The next one example here is in the U.S., Lansing, Michigan. Michigan is one of the states. That's the city of Lansing. Lansing Board of Water and Light. That is a small utility, supplies both water and electricity to the customers. They had to pay a $25,000 ransom to restore its network. They had nearly $2.4 million in recovery costs. You can see that in that link. And it is basically when they opened up their computers, screen saying that you got to transfer the money through Western Union, so on, so bank account, which might have been money might have been taken out some other country. You transfer it, the money is gone, and then they'll give you a key to open up the computers. So these ransom attacks have been happening quite a bit lately. So it is important to guard against these kinds of stuff. The next one is a Trojan Horse, is an attack vector or a mechanism. You might have seen when you're navigating to the web, a lot of times you probably get hit with the Trojan Horse kind of an attack. It's an attack vector or a mechanism to get malicious software installed on victim's machine. They appear to have a useful function. They look like a normal thing, like an Excel spreadsheet. You go and click it, then it put in the Trojan Horse virus on the computers, and then they will be doing other things rather than what the intent was. As an example, watering hole attack, to install a remote access Trojan rat, and so it infiltrates the vendor server. So basically what it does is it looks at the activity of this particular user. Now, let's say you have a power company and they have a lot of one of the manufacturer's products. What their engineers will do whenever a new firmware comes in, they go to their website, download the firmware, put the patch in the relays or controls or whatever. So this particular hacker would learn that this particular power company is going to this particular website all the time, and they probably have all kinds of firewalls and everything, so they cannot attack them directly. So they go and infect the server of this other company that they're downloading the information. So when you go there to download it, the virus comes along with it, and then now your computer is infected. So if you got a vendor's web server, you got number one here, the hacker attacked this one. So this guy engineer downloads it from there, a config software. Now the computer is infected. He takes it to the substation and then connects it to their LAN. All the computers and other machines inside the substation now got infected with that virus. So that's how you jump the air gap too. Basically, it gets into the computer. The physically somebody who has complete access, badges, secret clearances, and everything, he walks into the substation with the virus in his hand and then puts it in. Now all the pieces get attacked. The last one is a keylogger. Keyloggers are specialized malware that monitor the computer and record anything that is typed on the keyboard, transmitting the data out to the attacker. And that's why generally the passwords I don't type most of the time. Sometimes I do have to. I have another file which is encrypted file. I saved on a computer. I go there and copy and paste. But if you're punching the keys, if there is a keylogger on your computer, and every keystroke is stored and then sent it to the hacker, and the hacker has your passwords and other keys now. So then he can come back and get on. So keyloggers are dangerous things. So here it shows an engineer on his computer, the keylogger is installed. And then once this guy gets all the passwords through keylogging mechanism, he goes and directly goes there and bypasses the firewall because he has the passwords directly, and then he can attack these things. AICTE is an organization based on inside the US. It's one of the departments inside US Department of Homeland Security. We have AICTE, it is called Industrial Control Systems Cyber Emergency Response Team. Most of the industrial control systems, electrical power infrastructure also comes under the same thing. There is a reporting mechanism. So they actually conduct all kinds of tests on products also, and they report any kinds of weaknesses, vulnerabilities, and then the vendors go back and fix them, and then they repost them with patches and stuff like that. So they have a pretty good monitoring mechanism. They got, if you go to their website, you will see all kinds of things. And if you're using a product, if it has any vulnerability, and if you go there and search, you probably will find something saying that you got a new firmware. And you can see these pure wipers. Wipers means they wipe out your hard disk or any kinds of memory that you have in the product. Prime example is a kill disk. If you hit a kill disk, your hard disk will be repartitioned so that it's completely wiped out. You can't even restore what is in there. The rest of them are similar. Some of them have a little more than just wiping out the hard disk, like a White Rose, Dark Soul, various other wipers. There are multifunctional wipers. They'll wipe the hard disk, but also do additional damage. The black energy is one of them. The Ukrainian attack actually used black energy. Shamoon and Distract and several other ones. So what will they do? Your protection logic, SCADA software, backups, historian, any configs, all the stuff can be wiped out if you're hit with one of those. That virus could have come as an email attachment to the control system operator who is opening up his email and clicking on an Excel spreadsheet that he thinks it is something that one of his colleagues sent it, because they pretty much camouflage the email addresses. When you click it, it puts it onto the machine, and then it wipes out the stuff. The last one in this series is denial of service. This is another big one. It is a kind of it overloads the entire network and it replicates. It's like a botnet. It's called botnet master controller. And then it sends so much traffic in there so that the genuine traffic can't even do anything. It's like programming a computer to dial a telephone number every few milliseconds so that nobody else can get through. That's why it's called denial of service attack. The genuine traffic will not be able to go through. The other one is a phishing attempt. This one, again, the victim sends user credentials, the passwords and other stuff. The hacker actually preyed on him, saying that he camouflaged himself as a good guy, and then now he sends the information. There are a lot of scams going on in the world right now. Even in our own company, we were scammed. Somebody sent a text message to one of my employees as though I am sending it. And then they went them go and find some gift cards they wanted them to buy. They bought like a few $1,000s worth of gift cards. And then I was instructing as though I was giving gift cards to employees and scan them and then text me. So within 15 minutes, all the gift cards were cashed by a hacker someplace. And then the guy comes back and then says, you told me not to tell anybody, but I just finished and I sent you everything. And I told him that was, he got spammed. So it happens everywhere. So this is a very big spam that happens. So here, this guy is trying to see if I can hook somebody on. Finally, this guy says he thinks that he's the right person. He puts the thing into the computer. Now he goes back into the substation and he jumps the air gap. That means all the firewalls, whatever you have, security mechanism, physical gates, everything, because the person has access and took his laptop in there. So this is called electronic security perimeter, but physically he's walking into the perimeter, so he jumped the air gap there. The next one is social engineering. Again, you're convincing the IT department to reset a password. As though you are the genuine employee, you send an email saying that reset my password. And then he resets it. And then this guy gets the email, he clicks the link, and then he gains access. Attacker poses as a network admin and gains access to PSP, but that's a physical security perimeter. He probably created a fake badge and then goes there and then say, I'm the admin, and they allow him to go into the computer room in the night, and then he gets full access and reads all the codes and everything. This is an example of altering software on a smart inverter, which is a solar panel, rooftop solar panel, commercial or residential. Generally, they use a cloud-based management, code on a device to detect faults. That means there is a software that is written on there to detect faults. A remote voltage and frequency control regulates energy flows, and it is dispatchable. That means the utility can say, I want more power, it will go up. If a hacker gets in, he can cause havoc on all these things. He can change the frequency, change the voltage, and cause damage to the connected loads. This shows here what is the impact of having such a thing and what is the probability of such an attack. And if it has all the security mechanisms, the probability will be very low. If you don't have security on the communication ports, the probability of attack is pretty high. This is a GPS spoofing. If you're using PMUs, where global positioning satellites are sending time sync signals. However, if you have a hacker who is nearby, near a substation or a power plant outside in a car, and he's sending these signals much stronger than the regular GPS, now the PMU is getting a new coordinates. And then now the sampling is done differently, so it looks like there is a 50-degree phase angle between the other side of the transmission line and this side. It thinks there is an imminent problem, it disconnects the, opens the breaker, causing a blackout. So that is possible by hackers. This one is a state estimation. And if you're reading megawatts, and other stuff remotely through communications, and the state estimation can have a very bad samples and then do all kinds of other stuff that you don't expect. Somebody was telling me that it's very easy to fool some of these unit commitment programs, because a lot of them depend upon the load that is there presently and the predicted load in the next 3, 4, 5 hours. So they can decide whether to commit a large power plant like a fossil plant, because it takes like a 12 to 24 hours to bring it on and then shut it down. And so if you send, or if you corrupt the metering data and send the wrong data, all your unit commitment programs will be gone. So that you can cause, people think that you can only cause cyber disruptions if you open close breakers. But just by infecting the metering data can also cause disruptions. I was telling you about social engineering earlier. If you click on this web link, I think that you have a PDF, and you will see there is a little company, power company. They hired a penetration testing team, and then they followed them behind with a truck, I think. And then this team, without detection, they were able to jump the fences of securities, physical, electronic security. They were able to hack into the passwords, everything. They were able to do a lot of damage. Basically, the power company figured out that they don't have any security. This is like a half an hour long video. It actually physically, they recorded the whole thing, how they hacked in. So it is a social engineering is a big thing lately, which is causing a lot of virus attacks. Let's look at the assets. What are the different assets, cyber assets? So if you look at physical assets, you got laptop, computers, switches, media converters, firewalls, radios, RTUs, relays, meters, PLCs. On the hardware side, you may have I/O cards, network cards, CPU, RAM, and physical ports. The software side, user applications, EMS, HMI, file transfer, Apache, etc., and protocol parsers and converters, and application programming interface or API, and software libraries and tools. Recently, we got a notification one of the DNP library we were using has a vulnerability. Now you got to go back and get a patch from them and download it, or update our firmware, put it onto our website and inform all our vendors so they can get that patch and then update the firmware. Otherwise, it is vulnerable to the attack. Data in all these devices, settings, configuration files, stored binary and analog values, sequence of events, digital fault recorder data, usernames, passwords, hashes, IP tables, all this stuff becomes a cyber asset. What do all these devices have in common? Both hardware and software. The hardware-wise, RAM, hard disks, solid-state drives, CPUs and I/O cards. And then on the software side, you got operating systems, Unix, Linux, Windows, and proprietary operating systems. And then application programs, whether it is a fault detection and operation logic or protocol parsers. People have been using lately field programmable gate arrays, which are programmable. And if the hackers get in and reprogram that, it will completely pretty much becomes dead or does wrong things. And then you got the firmware that goes back into any of these logic things that we talked about. And you can upload the firmware to corrupt those devices. Talking about protocol communications, if you're familiar with IEC 61850, it has a 7-layer stack. An application layer, presentation, session, transport, network, data link, and physical. So if you want to transmit data from one location to another location, let's say you got a relay connected to the CT and PT, and relay sampling this data, it wants to send the data to a SCADA system so that it can archive and look at the trends. The data gets transmitted either through physical wire or wireless means. That piece of data, it gets attached with the application header, and this whole packet gets a presentation header attached. By the time it comes down, the packet becomes very large, and that packet gets transmitted. When it reaches on the other side, there is a physical, it strips off the physical side, it strips off the data link header. Finally, this application gets what this application is looking for. And so the data gets finally transmitted to the other side. In this process, people can tap into in the middle, and if they know it's a 61850, they know the headers and how the packets get encrypted, they know where the checksum is. They can figure out on how to stuff the bits and then recalculate the checksum and put in the middle of the packet so that when it gets to the SCADA, the values are wrong. Protection and control of the digital grid. So if you look at the physical flow of power information, identity, the function is identity. The loads, transformers, breakers, cab banks, these are all physical equipment, and how do you identify them? Protect. How do you protect the physical assets from faults and other things? You control them, protective relays. You may have monitoring RTUs, EMS, and settings and configurations, various other things that you have. How do you detect faults and other things? Relay protection logic, and primary and backup protection, and maybe some SCADA may be involved. How do you respond once you detect it? You isolate the fault, and you reclose after the fault is cleared, and you go to lockout if the fault cannot be cleared, and you can open or close the breakers, and then also respond with a sequence of events. And once that is done, how do you recover? If you open the breaker, you reclose the breaker, and then you have the watts and watts returned back. Same thing looking at the cyber infrastructure, identify the cyber assets. I think we talked about what the cyber assets are earlier. How do you protect the cyber assets? You got controls put on them, firewalls, data diodes. That means the data can only flow in one direction. That means you can only read the data, you cannot write. IEDs and configuration files. And detecting, how do you detect it? You got intrusion detection schemes. You may have other detection mechanisms inside the relays, or you may have a physical detection. That means somebody opens a door, there is a switch in the bottom someplace which sends a signal, and maybe recording a camera nearby, so the other side you will know. Respond, how do you respond if you detect intrusion? You immediately remove access and disable those passwords or whatever you need to do. Recover, how do you recover if you have an attack? You may have backups that are stored someplace. You need to bring those backups, or you replace if it is completely wiped out. Happened here. Okay, so the vulnerability handling and incident response. Minimize the risk, that is the biggest thing. There are certain responsibilities for the vendors, and there are certain responsibility for the utility. The vendor responsibility, or it's a cultural change. Accept that vulnerabilities exist. Having a vulnerability is acceptable because the hackers are always learning, and sometimes they're ahead of you people. So there will always be an attack. But how do you detect, and how do you stop, and how do you stop future attacks, and how you recover? That's important. So vulnerability is acceptable, but improperly handling them is not. Formal processes and policies are important, proper communication at the right time. You don't want to communicate after 3 months. By that time, the whole thing is infected. So once you detect it, you got to act quickly. Utility responsibility. Awareness, that means continuous monitoring of product updates to ensure software versions are assessed and implemented. If you detect a vulnerability, if the vendor informs the utility saying that I have a vulnerability in the device, this is the patch, but if nobody is monitoring that line, and if they don't update the patches, obviously there will be damage. And cultural change, accept that vulnerabilities will require patch and firmware upgrades. Sometimes when the system is running, you may not be able to do it. If you have a primary and backup, you can do it. If not, then you may have to shut down the system. So I think so much for explaining about physical and cyber infrastructure, different risks, different cyber assets, and how do you manage once you have. So now let's talk about what the industry has been doing for a number of years, industry standards and cybersecurity. These are all various standards that are being worked on by various standards developing bodies. NIST 7628 is a guidelines for smart grid cybersecurity that is developed by a National Institute of Standards and Technology in the United States. This is a federal government owned organization. And then IEEE, which is an organization, worldwide organization. I work heavily in IEEE with various groups, including cyber and also protection and control groups. And IEEE Standard 1686, it was developed back in, I guess, revised in 2013. And there is a group right now working on revising this. It's a standard for intelligent electronic devices cybersecurity capabilities. If you have IEDs like relays and controls, this one defines and what kind of a basic minimum requirements that you have in order to secure that. If you have a serial link, 232, 485, those kinds of stuff, with an IEEE standard 1711 for using for IEDs or SCADA communications. They're being revised right now. And then IEEE standard C37.240, cybersecurity requirement for substation automation, protection, and control devices inside the substation. That is actually under revision. It is again within our group, PSCC and IEEE PSRC. And you have IEEE 1815. If you're familiar with DNP, that is the main protocol used in North America. In fact, 61850, very few people use in North America. You can count with your fingers which utilities use. I would say 90% people use DNP, and a lot of power plants use Modbus. And so the DNP does have a secure authentication. And then for DERs, distributed energy resources, which are solar, wind, and all these, IEEE 1547 group just started this .3, which is Guide for Cybersecurity of DERs Interface with Electric Power Systems. If you go to IEEE website, you will find a lot of working groups and other stuff, activities that are going on. And you're welcome to navigate our websites and then download certain documents which are free. Others, you may have to purchase them. And also, if you want to participate in any development of this, if you're really interested, you could, some of them allow you to remotely participate, but a lot of them may require you to physically travel there. Of course, with COVID, you don't have to travel, but you can contribute to these standards. IEC 62351, this is the standard suite for if you are using 61850, it provides you how you actually provide security for those. It has various parts in there. And then the last one is NERC, which is a North American Electric Reliability Corporation, which works under FERC. The FERC reports to U.S. President, basically the overall organization to keep the reliability of the electric grid inside in North America, both U.S. and Canada combined. It has the authority to go and audit and make sure that the people are following proper cybersecurity processes. If they're not, they can be fined up to millions of dollars, the utilities. And the several utilities got fined because they weren't following some of the security standards that they need to, causing power disruptions. So I provided in the slides a little more information about the scope of this work that is being conducted by IEEE PES Power System Communications and Cybersecurity Committee, PSCC. We're actually going to be meeting in September, the week of September 21st to 24th, remotely or via web. We just finished up our schedule. So if you go to PSCC website, you will see some of these groups working. You can join remotely. I think there may be a small fee to pay, $35 or something like that. But you can attend week-long meetings, a lot of discussions that are taking place, and you'll get to know what the kinds of things these people are talking. These are all the groups that I was listing here. I'm not going to go through each one of them. These are the NERC-CIP standards. NERC-CIP standards are basically critical infrastructure protection standards that have to be applied to any bulk electric system in North America, whether it's a power plant or transmission organization, all the way to the distribution substation level. They have to follow, there are about 14 different parts in there: electronic security perimeter, incident reporting and response planning, configuration and change management, communication between control centers, supply chain. This has become a very big thing lately. Within the last few months, our company has spent a massive amount of time trying to look at what chips are there inside the microprocessor, where the chips are made, where the foundries of those chips, are they coming in from any countries that are not listed as safe countries? And if it is, then we have to find the chips that are made in the safe countries. And US President has created an executive order recently that requires any electrical infrastructure companies, they have to buy the products only from certain countries. They cannot buy products from other countries where there is a cybersecurity risk. There are a list of countries that are available. I'm not going to say those things here, but you can find them on the websites. Sorry. Okay. So all these parts basically go through in detail how you secure electric power system all the way from generation down to the distribution substation level. So let's talk about the electrical power side. I talked so much into the bits and bytes so far. Let's talk about electrical power side and what we are going to be discussing here. Concerns on cybersecurity, protection, and control IEDs. Modern distribution systems incorporate IEDs which communicate with the distribution management systems, or DMS. The protection and control IEDs and DMS typically send commands to open close breakers, reclosers, and switches. So this distribution management system is continuously scanning thousands of devices on the distribution system. If you're talking about a volt-var control system on a DMS, you may be talking to 3,000 capacitor banks on your system, maybe 2,000 transformers on your system, and trying to send commands to raise lower tap changes, or open close breakers, reclosers, all kinds of stuff. So these commands that are being sent back and forth through communication channel, if a cyber attack happens on the communication channel, they can send commands that are not intended and open close breakers. If you talk about power generating plants or transmission substations, big ones, generally those are physically protected with a maybe chain link fence with the cameras or a security guard standing there, but distribution systems are not. Distribution small substations, or if it is outside the substation equipment, it could be hanging on a pole, could be at eye level, or maybe with a ladder you can access it. There may be a control cabinet. You can break open the seal, open the cabinet, connect your laptop to an Ethernet port there, and you can gain access if you're a hacker. So that's where the bigger problem is. The distribution systems are not as secure because there isn't much a physical barrier. This one I added, I'm not sure if I will have a time or not. The copy that I sent you wouldn't have, just to show you how complex the modern distribution systems have become. This is a flizzr in the world of DER. I'll quickly go through a few slides here. So distribution system used to be relatively simplistic, predictable, forecastable, a limited visualization needed. Then came the DERs, created a mess pretty much because so many of them getting connected to the distribution system. PV, solar, traditional energy storage, electric vehicles, and demand response flexible loads. So in order to improve the reliability of electric power system, especially in the United States, you have feeds coming into the houses from multiple places. So you got 3 substations here shown, and they're connected to all these loads. And towards the end, there is a link between these. Suppose if you have a fault, that section can be isolated, and then you can feed the power from the opposite end. Things like that. So is quite a bit of work being done. There's a massive investment that are taking place to install reclosers, sectionalizers, and switches along the distribution feeders. So if you take an example, you got a lot of solar, let's say a lot of houses have solar, and this light bulb indicates a load, and this is solar generation there. Then you see this is a battery storage, came up. Then you got electric vehicles. And then you got temperature control like thermostats. Basically, you have an air conditioning unit, or if you have a swimming pool in the backyard, like the one I have here, or you got water heater, and the utility can actually remotely sending wireless commands to control all these equipment so that they can pretty much shave the peak off. That means for the next 10 houses, I'm going to shut off their water heater for the next 5 minutes. It doesn't cause any problem doing it. I'm going to switch off their pool pump. For the next 20 houses, I'm going to switch off the next 5 minutes, the next 5 minutes. That way, you can actually shave off the peak load. So that has been done heavily with these kinds of techniques. If you have a fault in the bottom, you clear. Basically, the substation breaker opens, and then there is some all the battery storage and other things were disconnected, and now you detect the fault and then restore the power looking at the capacity of the breaker, restore the power on both sides, and then only the faulted section get isolated, everybody else gets the power. Now let's say the fault again. Now, if the capacity of the breaker there is small, like only 60 amps, earlier it was like much bigger. Now you have 90 on the other side. And now what you do is you bring in battery storage and then use your switch off other loads. By doing that, you can reduce the load because you're supplying from the solar. Reduce the load again here, reduce the load again here. Now your capacity at the end is much higher. Now you can close that breaker and then you feed rest of the stuff. This is all done through communications. By having various communication media at various devices, you automatically reconfigure using Flizzr the entire circuitry so that the reliability of the power system can be improved dramatically. Several examples here it shows, but I'm going to skip through this. It shows you microgrid also here, how the microgrid can sustain by frequency control and other stuff. Do this. Okay, now let's talk about Ukrainian attack. What happened in Ukraine on December 23rd? Okay, you got 30 minutes, so I got to speed up. I got a lot of material to cover. So somebody sent an email with a malware outside the country it came from. One of their adversary countries it came from. I'm not going to name them from various reasons. Approximately 9 months prior to the attack, the hacker accessed the critical systems, SCADA system, HMI, operator PCs, etc. Telephone denial of service attack also prevented calls going through in and out. Control centers UPS had a firmware. They went there and shut it down. The UPS was shut down remotely from another country. Altered firmware at substation. There are a lot of control devices. They were able to figure out how to put them in the remote firmware update mode. They pretty much did a brain surgery. So that means those devices don't communicate anymore. And on exit, they implemented kill disk. So after the damage, they pretty much ran kill disk virus. That means it wipes out the complete hard disk, nothing left. As a result, you got 710 kV and 2335 kV dead substations with 225,000 customers lost power for 6 hours. And the operators, they said they were blinded. The operator was sitting in the computer watching something. All of a sudden, his mouse started moving, and he didn't touch it. So he thought some computer crashed. And then it goes to a breaker symbol, and then clicks on, and then say, do you want to open the breaker? And the message pops up, and then the mouse goes back and clicks yes. The breaker opens. Then operator got scared and then tried to grab the mouse, but he was already logged out because the keyloggers from this other country, they accessed this thing and they logged him out. Like that, they did it all the breakers, completely making everybody dead. And then they did the TDOS attack, tenfold denial of service attack. So nobody could get through. So now all the dead controls in the substation, they can't remotely do anything. They physically have to drive to each substation, manually close the breakers to restore the power. That's why it took 6 hours to do it. So it is one of the first of a kind cyber attack in back in 2015. And it was, again, as I said, black energy virus and kill disk. It was called Sandworm. If you Google Sandworm, you will know where it came from. Then in 2016, Ukraine was attacked again. It was using Industroyer and cache override. These are a control system like PLCs and others, they get attacked. And these actually are known to attack IEC 61850 and 60870-5 protocols. And so they're also meant for products in a substation. So you'll see the network disturbance, malware, cyber attack, unauthorized persons, and then the infected USB disks going and putting onto there. That's why a lot of people don't want this USB stuff called transient cyber asset, it is called. You go there and put it in, and then all the stuff it is in there gets infected inside the substation because you jump the air gap. Infected notebooks and data stormed by faulty devices. Let's simulate a cyber attack on a World War control devices. So if you look at a typical World War control system, you got a substation, you got a transformer, has a tap changer, and tap changer main purpose is to adjust the taps in such a way to keep the voltage in India at like 230 volts to all the customers. And if the load increases, the voltage goes down, the tap changer increases the tap. If the load decreases, the voltage goes up, the tap changer decreases the tap, so that the customers are always getting around 230 volts plus minus 5%. You also have capacitor banks. If the power factor becomes bad, that means heavy lagging or heavy leading, the capacitor banks can be switched on and off to keep the power factor to unity to reduce the distribution losses. Distribution losses amount to several percent, and if you can help them to reduce, you can save millions of dollars. So that's what the IVVC system or a Volt War optimization system does, but it uses heavy communications back and forth. If your communication system is attacked by a cyber, you can get into trouble. So let's simulate an attack. This tap changer, let's say during the nighttime, it's actually worse than daytime, because nighttime the load is light, your tap changers are on the negative end. That means maybe 8 lower. If it is 16 lower, you're minus 10%. 16 raise, you're a plus 10%. From 8 lower to 16 raise, if you go, you increase the voltage by 15%. So if you have voltage regulators in series, that also can be raised. And if you have capacitor banks, generally in the nighttime, because the load is light, the capacitor banks are off, you can bring them on, the voltage goes up. So if a hacker hacks into a distribution system and then raises the taps and switches on the cap banks, you can have 30 to 35% over voltage. Imagine having a 300 volts on a 230 volt circuit. All your TVs, other air conditioning systems, and other refrigerators, all the electronic equipment get fried when you have such a voltage. It's very dangerous. Also, the local distribution transformers that you have, which will bring down from 11 kV down to 230 volts, all those transformers with a high voltage, if you look at the magnetizing BH characteristic of a transformer, you get large magnetizing current. Typically, it is less than 1%. At those high voltages, you hit like 60, 70%. That is still less than a full load current, so the fuses won't blow, but the transformer gets heavy overfluxing, and then it heats up the core, and after a few minutes, they start popping. That means they will get destroyed. You'll see fires start coming up from the poles. So if the hacker does a coordinated attack, you're talking about thousands of these distribution transformer can be failed. A lot of utility consumer electronic devices can fail. So the damage can run into millions, if not billions, if it is a coordinated attack. So that's why it's very serious if we have a cyber attack on a distribution system. It just goes into more. So now we talked about the basics of cybersecurity. We talked about some of the physical attacks that took place cyber-wise. And then we talked about a simulated cyber attack, what happens. Now, what do you do about it? How do you secure? So I'm going to take one small piece. When we teach a cybersecurity tutorial, we do 8 hours, but we're doing it an hour and a half. So I got to rush through a lot of topics. So I picked one of the IED, a controller that controls capacitor banks. The similar control, maybe a controlling tap changer, or controlling a voltage regulator, or controlling a recloser, or maybe providing protection from a feeder. It doesn't matter what the device is. Any of those devices have to have security mechanisms. So some of the basic mechanisms that actually the reason why we designed this on these products way back 8 years ago, a utility that feeds some of the critical governmental infrastructures in the United States came to us and then said, we feed most sensitive installations and we need a lot of cybersecurity stuff into your product. So we spent 14 months, spent more than $1 million designing. So as a result, you got IEEE 1686 standard for authentication, and secure DNP we added. Intrusion detection. If somebody opens the door of a cabinet, automatically SCADA gets information saying that somebody intruded to it. And then you got centralized authentication, authorization, and accounting. That means if you have passwords on 3,000 devices, it's very difficult to manage to drive to each place to change passwords. So if you're able to control these passwords remotely on a server, then the device has to authenticate with the server. And if you have to change the passwords when you lay off several engineers or technicians who have passwords, all you need to do is go to that server and then change the password, one location. So you don't need to worry about. And if you're using internet as a means of transporting packets, you can use a VPN tunnel. So we have a complete encryption. All the packets get encrypted and decrypted at the end so that nobody can eavesdrop and trying to figure out what those packets are and try to infect those packets. So 1686 forces you to do strong password construction. It's not just a number, 4 digits or something. You have to have uppercase, lowercase, special characters, and longer passwords like more than 8 characters or something. No undisclosed bypass backdoor. Olden days, we used to do that. Somewhere in the instruction book, we say, by the way, if you forgot passwords, you press this key, that key, and this key, then you get access to the factory. You can't do that anymore. Multiple access level. This is basically the information on a need-to-know basis. Depending upon the role of the person, you allow certain features. A non-modifiable audit trail. That means whatever password that was used, or when it was used, what did he do with that password? Did he change settings? If he changed, what setting is changed? All that stuff has to be logged as an audit. And then alarm generation. If somebody is trying to hack into this by putting a wrong password 10 times, then you send an alarm saying that somebody is trying to intrude. So this is all the different audit trails. And then these are again alarm events. And this is how the typical screen looks like. These are all the different permissions we're talking about. This is how you manage the users from the administrator. And when you're typing in the passwords, and it tells you whether you're meeting the requirements for the password or not. And this is a role-based permissions or role-based authentication. So based on the user's role, you can say he's the only guy who can change the firmware. And maybe he can only read the files, but he can't write the files. Things like that you can set based on the type of users that you have. And this is, again, DNP secure authentication mechanism using secure hash standard. This is built into one of our products. This is a physical intrusion detection. If somebody opens the door by breaking the seal, there is a little micro switch that gets connected to the controller, immediately it sends operators, somebody just intruded. If it was not an authorized access, they immediately dispatch the police or the utility crew to find out what's happening. Let's talk about password management. We talked about centralized authentication and authorization using Radius. So Radius, it does three things. It's called AAA. It does authentication, authorization, and accounting. So it authenticates the users or devices before granting them access to a network, making sure that he's an authenticated user. And then based on the services that are allowed, it authorizes those users with the devices or certain network services. And then finally, accounting for uses of those services. What did he do when he came? All the audit that I talked about. This is how you configure those Radius servers. So basically, somebody goes to the substation, punches the button in the front panel, or uses a laptop to get access to a specific service, maybe a relay or a control. As soon as he punches those, the Radius client inside sends a signal, maybe 300 miles away, to a server which is housed in an underground bunker someplace. And then the Radius server looks at the credentials, and if it is proper, then it grants access. So he will be able to change settings, do whatever. Let's say he's a disgruntled employee. He slices this fiber because he knows. Then you probably put another secondary server, maybe 200 miles away in an opposite direction. And if you don't get any response, it tries to get it from here. If the network is down, then you may have a local authentication server so that you can at least get a grant of access. Otherwise, what will happen? Every device on the system will go stale because you can't access them anymore. There is another protocol called Ldap that's being heavily used by a lot of people nowadays. And it is similar to the other one, but it is much simpler. It doesn't do the auditing thing that we talked about. It does authenticate using a directory service. So there is a lot of information here. I'm going to skip through quickly here. So here, when you're trying to authenticate using Ldap, it sends the signal. There is an Ldap server here. It tries to check the credentials. If the credentials are met, then it allows the database to retrieve the data. If they are not met, then it goes back and then saying he's not an authorized user using that API. Let's figure out how you secure data that is going on internet or a public network. If utilities have their own private network, there is no problem. You don't need to encrypt nothing. But if the data packets are going through the public network, that if you use the encryption in the modem, you're pretty secure. Not so, because the modem encrypts the data, it decrypts it here, it goes out. But the cable that is connected from the modem to the controller is not encrypted. If a hacker comes in, disconnects his cable and connects to the laptop, his hacking message gets encrypted and decrypted, he gets through the network. So that's why you got to have the encryption algorithms embedded inside the chips. So he has to take a chainsaw and cut to figure out what is inside. So end-to-end encryption is very, very important. So IPsec, what are the advantages? Confidentiality by encrypting the data. Integrity, routers at each end of a tunnel calculates the checksum or a hash value of the data. Authentication, you can use signatures or certificate, so only valid signatures are allowed. And so IPsec is designed to provide interoperable, high quality, cryptographically based security for both V4 and V6 LAN. All these while still maintaining the ability to route through an existing IP networks, which may not be secure. Another thing, given enough time, any encryption can be defeated. There are a lot of hackers using very powerful DSPs with maybe 30 or 40 processors, like some of the graphics cards that are used in gaming hardware. They're using some of that stuff to hack the basically crack these passwords and encryption algorithms in a matter of minutes or days. So that's why you have to change the keys very quickly at frequent intervals. This shows you, I picked it up from Wikipedia, but shows you very simple using colors how the key exchange mechanism works, Diffie-Hellman key exchange. It uses the modern algebra prime number math to very simply explaining how the key exchange mechanism works. If you're a college student or a lecturer, you can easily understand if you go through that. So just to explain about this key policy, that means you basically have a public key and a private key. Public key is exchanged on the wire, but you have a private key, and using the private key and the public key, you can encrypt the messages, and you have the algorithm to decrypt once the message comes. But you also have to have a lifetime for that, 2 minutes, 2 hours, 3 days, depending upon the complexity of the key you can select. Once the key is exchanged, the channel is set up. Now the IPsec, the tunnel, the data that is going through need to be encrypted. There are various algorithms. There's a DES, AES, and I think the triple DES is suggested here because DES has already been hacked by a few countries. So that's why the Department of Homeland Security suggests using triple DES. Policy lifetimes, how long the key is valid, you can set. And then these are certificates. You can also use the digital certificates instead of using the previous mechanism that I talked about. As you can see, the amount of work that is required to implement these cybersecurity algorithms is tremendous. You got a TCP IP stack, a security policy database, and then you got IPsec input-output, drivers, encapsulation, decapsulation, crypto library, all the hashing algorithms, a dozen different encryption algorithms, they're all put in the library, authentication headers. This whole stuff took about 14 months for us to develop. And then anytime you put encryption, the data packet becomes much larger. That means the throughputs gets affected. So if you take no encryption at all, let's say you have a minimum packet timing is 0.6 milliseconds and average is 2 milliseconds. If you put the most complex algorithm and large data, you'll see almost like more than 10 times the time it takes. But you can find reasonable algorithms, maybe it's double here, 2 milliseconds goes to 4 milliseconds. You can manage, but the security is important. So you need to figure out what level of security, what level of algorithm that you need to use, and how long the key should be valid. They all can be determined. Finally, in concluding, I would say that the modern protection, monitoring, and controls in electric power systems with advanced communications are vulnerable to cyber attacks. IEEE, IEC, NERC, and various other standards developing bodies are addressing all these things. And if you talk about 20 years ago, none of these standards exist. But nowadays, standards are available. But the hackers are actually a step ahead. Anytime you come up with something, they're already hacking those things. So that's why constant updating of patches and stuff is very important. So it's important to consider applying these standards to IEDs, intelligent electronic devices that are being integrated into substations and federal equipment to provide secure communications. Advanced cybersecurity features such as radius for authentication, authorization and accounting, and IPsec VPN tunneling for secure communications via shared network can be embedded into protection and control IEDs, which will provide secure communications inside as well as outside the substation. I do want to thank a couple of people. I took a few slides from them. Some of my colleagues, 3 of us actually teach cybersecurity tutorials. One is Dr. Nathan Wallace. He works for Cyberical and one of the company's cybersecurity firms. And then Steve Kunzman, he works for ABB, which is recently bought by Hitachi. He's ABB Hitachi. He's chair of a lot of these PSCC committees. I knew him for the last 30 years or so. So that pretty much concludes my presentation. We got 10 minutes. I thought I was going to leave 15 minutes, but I had to rush towards the end. Any questions anybody has? I'm going to go in.
So being the faculty, they are worried about the Zoom platform for learning, teaching learning process. They have the questions on that. So how secure
okay.
is the Zoom app?
Okay, that's a very interesting question. So we actually went through the same issue within our company. We use something called Ring Central, and then we realized that the Ring Central uses Zoom as a mechanism. And then when we go through and looked at its mechanism, especially if the servers are located outside of your country, in some countries which are not very well known for keeping information secure, you can get into trouble because all the confidential information that you may be talking, of course, if you're teaching students, probably it's not any highly secure information. But if you're talking about military or police or those kinds of very confidential information, or nuclear power plants, you got one nearby to Chennai, things like that, obviously you have to be worried about if the servers for that particular, whether it is a Zoom or whether it is a Teams or whatever you want to call it, if those servers are hosted in rogue nations, yes, you can be worried about. I don't want to comment directly on Zoom. You can Google and find out which country it is hosted. The version of the software that we were using, Zoom, as part of the Ring Central, those servers are hosted in North America. That was guaranteed to us through a letter. So that's why we continue to still use that. But the standard Zoom might not have been. And you need to figure out where it is, or you have to talk to your service providers to make sure that those are within your country, not outside, So, okay, next question.
Participants, do you have any other questions?
Yes, ma'am.
Go ahead.
Sir, how will you evaluate the new security algorithm, sir? Suppose if you are developing any new security algorithm, how will you evaluate, verify, and validate the security algorithms?
Yeah, so what you're talking about is if you come out with new encryption or any of those kinds of new algorithms, how do you validate them? Obviously, most of these security algorithms have encryption and keys. The important thing is to securely store the key someplace. In fact, if we are embedding a security key in our company, only one person probably knows that, and we follow very high level of security. Any new algorithm that comes out, the algorithm may be public domain, but the complexity of the key that you use to encrypt using that complex algorithm, it makes longer to crack, whether it is in few seconds or few days or few hours, depending upon the length of the key that you have. It can take 100 years if you use very long and very highly encrypted. So the technology for encryption keeps going up as the time passes on. A lot of universities are working on this security, various encryption. That's why multi-factor authentication is also important. Multi-factor means there are at least two ways of verifying. If you're opening up a bank account, you probably get an email from them saying they'll click this link. So if you gave your email to them, they send you that stuff, and with your social, whatever the numbers, confidential information. And then the second way of verifying it, or maybe even third way of verifying it, you get a text message, then you verify back, or you have a hard key that you have to insert in a computer before you use. That is always better. Using only single factor is probably not a good idea, especially for highly confidential information.
Thank you, sir.
Okay.
Thank you, sir.
Okay, let me see here what other back. Yeah, I don't see any other question, but generally, I always say this when I give lectures. If I'm getting questions, that means you understood something, but not everything. If you don't have any questions, you completely understood everything, or you didn't understand at all. Okay.
Sir, I ask one more question, sir.
Yeah, go ahead.
Sir, you are having any testbed arrangement, sir, for evaluating the cyber security, cyber attack? You have any testbed arrangement in your company?
No, we don't. We're not a cybersecurity company. We are a protection and control company, but we have cybersecurity features embedded inside.
Okay,
We
sir.
have our own engineers test our cyber stuff, but there are a lot of other third-party pen testing or penetration testing companies. The Cyberical is one of the one that I was mentioning, Dr. Nathan Wallace. His company, they go to the sites and they do pen testing, penetration testing. So basically, the utility will tell them, go and penetrate my network. They use all kinds of ways trying to see if they can penetrate. If they do, they find vulnerabilities, and then now you go back and update whatever the patches or whatever you need to. Okay, so there is a question here called any open source software available for simulating DER cybersecurity? I don't think so. It's again, cyber. There is nothing like a DER cybersecurity. Every vendor, they do their own way of doing cybersecurity. That's the reason why 1547.3 they're coming up with certain basic security mechanisms that need to be incorporated into DER. Once that standard is completed, there probably will be a kind of a simulation. Something will be available where you may be able to test and see if you're able to penetrate those or not. But it is important that if you are able to hack into DER, you can actually change a lot of parameters inside. You can export power, import power, you can increase the voltage, you can change the frequency, cause all kinds of damages. So that's why DERs have to be highly cyber secure, especially if it is interconnected to a network. Okay, let's see here. I don't think any other question was there. I guess we only have 3 minutes left.
Yeah, maybe, sir, I think if at all the audience can send the questions later on through email, and he will be able to respond to those.
If they send it to your email address, collect them and send it to me, and then I will get a response back to you. So not a problem.
Yes, yes.
On behalf of KCG College of Technology, I would like to thank our distinguished speaker, Dr. Murthy VVS Ella, President Beckwith Electric Florida, for his informative talk on definitions of cybersecurity and the industrial standards on cybersecurity, details about Ukraine attack, cyber attack on distribution system, and how to secure electric power protection and control devices. I hope all the participants take away the technical insights shared today. Thank you, sir.
Thank you very much. I appreciate Dr. Samandan to contact me, and I hope I was able to share. I know I had to rush up some of the stuff, but I was able to share some of my experiences in North America, the kinds of things that we do there.
It was a wonderful presentation, and we covered almost everything.
Again, thank you. I think your name is Dhanalakshmi, or the lady that's speaking?
Dhanalakshmi, and it's Gayatri.
Gayatri, sir.
Gayatri. Okay, I'm sorry. So thank you again for moderating the session and giving back input back and forth. I appreciate your help here. So, Gayatri.
Thank you, sir.